Example 1 here on convex and concave curves is taking a look at characterizing graphs. So say we have a graph of the function f of x or y equals x times x squared plus 1. So I'm going to write this as f of x equals x times x squared plus 1. Okay, just so I can use f of x notation and f prime of x notation. So here, what we're looking for is the parts of the graph where the function is convex or concave and to find the points of inflection. So the first thing we need to do here is find f prime of x and then subsequently find f prime prime of x. So f prime of x, well, that will be equal to the derivative of f of x. So if we just expand this here, we get x cubed plus x. Okay, so f prime of x, well, differentiating this here term by term, we get 3x squared, and we get plus 1 there. Okay, and now finding f prime prime of x, well, that would give us simply 6x. Now remember, we're looking for here f prime prime of x equals 0. So in that case, we're looking for 6x equals 0. So therefore, the only solution we obtain here is x equals 0. So what that tells us then is f prime prime of x is less than 0 when x is also less than 0. Okay? And here what we have is a concave section. So this is a concave section. Okay? And f prime prime of x is greater than 0 when x is also greater than 0. And here, this will be a convex section. Okay, so convex section. Now when 6x equals 0, like we said here, i.e. x equals 0, we have a point of inflection since the curve changes from concave to convex at this point. So the function is concave for x being less than 0. It has a point of inflection at the origin, x equals 0, and is convex for x being greater than 0. Okay, so that gives us everything we need there for example 1 and gives us the solution to our example. Example 2 here on convex and concave curves is taking a look at stationary points of inflection. So in this example here, we're asked to show that the curve, which is given here on the screen, has a stationary point of inflection at x equals 2. So to do this, we need to find dy by dx and the second derivative. So here, let's find dy by dx first. So dy by dx, well, that means we're just going to differentiate y here term by term. Okay, so if we differentiate x cubed here with respect to x, that would give us 3x squared. So that's 3x squared, and minus 6x squared here. Well, if we differentiate that with respect to x, that will give us minus 12x. And finally, we have this plus 12x here, and if we differentiate that with respect to x, that would give us plus 12 there. Okay. We also now need to find the second derivative, so we're just going to differentiate dy by dx here with respect to x. So for the second derivative then, well, in that case, again, going term by term here, 3x squared would give us 6x. If we differentiate minus 12x, that will give us minus 12. And for the plus 12 here, well, as that's a constant, if we differentiate that, we just obtain 0. So now, what we need to consider is this value here of x equals 2. So, if we just start with the first derivative here, dy by dx, if we substitute x equals 2 into dy by dx, what we want to show here is that dy by dx is equal to 0 when x equals 2. That would tell us there's a stationary point at x equals 2. So let's substitute that in. So when x equals 2, here, dy by dx is equal to 3 lots of 2 squared, minus 12 lots of 2, and finally plus 12. Okay, and if we evaluate this, what we find is this is equal to 0. So that tells us there's a stationary point at x equals 2. So let's just note that down here. So therefore there's a stationary point. At x equals 2. Okay. Now let's consider the second derivative. So again, when x equals 2, let's see what we obtain. Okay, so when x equals 2, what do we obtain for the second derivative? In that case, all we do here, again, is we just substitute this into our second derivative. So that's going to give us 6 lots of 2 minus 12. So clearly that's just going to give us 12 minus 12, which is equal to 0. So therefore, what we can see then is when x is less than 2, the second derivative will be less than 0. Okay, so when x is less than 2, the second derivative will be less than 0. And when x is greater than 2, the second derivative will be greater than 0. So that tells us there's a point of inflection at x equals 2. And therefore, the curve has a stationary point of inflection at x equals 2. So we just note this here in the bottom corner in a different pen colour, just so we can see it's clear. So when x is less than 2, so this is corresponding now to the second derivative, then the second derivative here will be less than 0. Okay, and again, notice in a different pen colour, when x is greater than 2, then the second derivative will be greater than 0. Okay, and like we just said then, to summarise, that tells us the curve has a stationary point of inflection at x equals 2, like we're asked here. Okay, so that gives us the solution there to example 2 on convex and concave curves.